Hello, my name is Colin Go, and I'm from Physics 2211 Section C, and today I'll be talking about Lab 5, Pendulums. The purpose of this lab is to find the gravitational constant g using the motion of a pendulum, and also to analyze the motion of a pendulum using computational models. So quickly here, our results preview, we had our x and y graphs that we ran using our pendulum data. Additionally, we found g experimentally using that data, and we ended up with a constant of 8.1489. This is obviously slightly off from the actual value that we know of for g, but we'll talk about that later. So just an introduction to our main physics fundamental principle here. It's simple harmonic motion. This is the concept that basically is a similar theme amongst all these equations that we'll look at in a bit. So here we have angular displacement. This is going to be theta equals theta naught, or initial angle, times cosine of omega t. We also have the pendulum position equations here, which we calculated and used to find our graphs. And so here we have x position is equal to L sine theta t, and then y is L cosine theta t. Additionally, we have the angular frequency equation here, which is angular frequency equals to the square root of L over g, L being the length and g being gravity. And then our main and most important equation here is our period equation, where t equals 2 pi times the square root of L over g. So our lab setup here, our materials was an AirPod case, a piece of floss which acted as our string, a camera, the tracker software, and also a protractor within the tracker software. Our assumptions were that the system was isolated with no external forces, and that being said, our system was just the AirPod case and the surroundings were nothing else. And we also assumed that the floss was massless as well. And the units were meters and seconds. So just our lab setup here, we have our axes, and then also our calibration stick, and this is our bob or our AirPod case and the piece of floss that we tied. And this is acted as our pendulum. Here we have our tracking software with our data to the right. We have our protractor that we use to find the angle. And here we have our initial conditions within our GlowScript code. We have the length of the string equaling to 0.235 meters. Our initial angle in radians is 0.493928. Our mass was 27.9 grams, or 0.0279 kilograms. Our experimentally found g constant was put in here as 8.14. We have the radius of the bob for our visual, and then our time step here. Our equations, we have our position equations using the x and y positions we talked about earlier, and we just put this in vector form. And we also inputted our period and angular frequency equations, as you can see right here for line 47 and 50. We also found the period using the x position data. So we found two periods and we averaged them together to get an average period of 1.0665. And then we found our gravitational constant using that period. So we plugged in t, 2 pi, L, all our known values. We solved for g, and we end up with g equals 8.1489. Our computational model here, we had our loop running until 2.167, which is how long the video ran for. We have our simple harmonic motion equation from the very beginning. We updated our position. We updated the rod position as well. And then we also graphed our plots as well. Here is just the visual of our GlowScript code that we ran. We have our path of the pendulum. This is the bob, the string, and then the fixed point up here. And here we have the graphs that we outputted using our GlowScript code. So this is the x position. You can see the oscillation back and forth. Same with the y position over here as well. And so obviously our value for gravitational constant was off. So we wanted to find the percent error using just a simple percent error formula. So we took the actual value subtracted by 8.15 divided by 9.81, multiplied by 100 to get a 16.9% error, which is not too bad in hindsight for an experiment. But obviously we had some sources of error that caused that percent error. So we have external forces. We assumed obviously that the string was massless, and that it has mass, so that's one way. Additionally, there are air resistance and slight friction at the fixed point. Additionally, the human error is another source of error, just because our tracking for the center of mass for each of the for when we were using the tracking software is one way that the data could have deviated. So what if our equation for what if is going, or our discussion question for what if is going to be, what if we change the mass of the bob? So we made the mass of the bob some extremely large number that's obviously not realistic at all. But when we did this, we found that because mass is not included in this equation, it does not affect our g constant or the period or the motion of the pendulum whatsoever. So that is one what if question. And for our what does it mean question, we want to see here is how does the changing initial angle affect the pendulum's motion? Does it change the period or adjust the swing amplitude? And so this equation is for small angle approximations. So if we changed it by a little bit, it will not change anything. However, if we change the initial angle by a very large amount, then it would increase the period slightly. Thank you. That is all for our pendulum lab.